Okay, good morning, everybody. I hope you're enjoying your snow. I went out and shoveled today at about 5:15, and I had fun. It was a nice, clean snow. Light wasn't bad, but let's get on with calculus. Okay. Now, I told you yesterday that we had a very important group of lessons. So today we will be spending in class, even though we're going to be late. We'll still be working on that some more, but I expect you to really go through these, understand to not only just the concept, but the mechanics of doing these problems. So let's work on example number 2. Okay, example number 2. The rate of change of y is proportional to the y. When t is equal to 0, y is equal to 2. When t is equal to 2, y is equal to 4. What is y when t is 3? I don't know. I have no clue. So what am I going to do? First of all, I got to break down the problem. I say, okay, anytime I told you when you see that phrase, the rate of change of y, what is the rate of change of y? Now, we haven't really talked about t as being time, but yes, it is. It's time in this case. We're going to talk about it in that context, but t could be anything. The rate of change of y is proportional to y. When the area is 0, y could be 2. Okay, but let's work with time. That's where the easy one is. So let's put that together. First of all, I want you to say dy dt is proportional to y. Use the fishy symbol and translate that. Remember, that's the first thing is. That's what that mathematical statement means. And now we're going to incorporate the constant of proportionality. Okay, k. We typically use k. So there we have it. Now we're going to start out. Let's put some conditions we have. When t is 0, okay, we have 2, an output of 2. And when t is 2, we have an output of 4. You'll see where those will come in down the road. This is the first one we're doing with a little more obliqueness to it. So what do we do with separation of variables? Remember, dt's to the right, everything with a y to the left. Okay, so let's everybody march in their right positions, and we get dy over y is equal to k dt. Okay, so what's the first step that we're looking at? We know how to anti-differentiate the left. That's just going to be the natural log of the absolute value of y. If you don't remember the absolute value, you're going to end up having lots of mistakes. Okay, and then we have kt, and we're going to usually put our constant, our, our anti-differentiation c on the right side. We won't put it on the left. We'll put them all together. There's really two of them, but we're only dealing with one. Okay, and what's the anti-function for natural log? It's the exponent to the natural base. So we're going to take e raised to the natural log absolute value of y group. Remember, I want you to always group that. Always group that. Okay, I know you say why. Well, I told you a little bit why. So let's group this one. kt plus c. Okay, now we know what the e does to the natural log. It just undoes it. So we're going to go ahead and write absolute value of y on the left. And then what do we have on the right? Well, we're going to use our exponent properties to write this as e to the c, and then that's a number. We know e to the c is a number, and then it's e to the kt, and that's we got the variable in. And notice we have two things we don't know anything about right now. Okay, so we've gone through the procedure now. There's a number of ways to do this, but let's just go ahead and say, well, sometimes people might want to put in the values here. And I tend to say, let's solve this thing. We know that now we could write y is equal to uh, plus or minus c1 e to the kt. And why is that? We could say let c1 equal e to the c. Well, then we could say y is equal to some c2 e to the kt if we let um, plus or minus c1 equals c2. And remember, c2 could be a positive or negative number. So that's another way to write our justifications. And where does this come from? Okay, so that comes from the absolute value. Remember, we have to plus and minus. Sometimes we'll write, as I showed you in class, we'll say C2 absorbs the plus or minus C. So C2 absorbs, absorb, absorb, adsorbs the ABS. sine, sines. Okay, something like that. Okay, so we'll get into that a lot clearer. So we've got an equation now. We've solved our differential equation. What is this differential equation? It's what? It's an equation for a family of what? Slopes. Okay, we just know about the slopes. What do we know now? We know the curve. But what does the curve have? The curve's got a lot of things here that we don't know anything about. C2 we don't know, and K. So let's use this initial condition now. Okay, 0, 2. So we know that Y, let's go in here now and go into the like a work zone. And let's put 2 as Y, and we don't know C2, and we don't know what K is, but we do know that T is 0. Makes it nice. You'll usually find something nice here. And that value is 1 then. So that means I know now C2, so we're going to say that is 1. So that's 1. So then C2 is equal to 2. Okay, so I know a little bit more. So I know now that at least lets me write Y is equal to 2e to the kt. Okay, I'm one step closer. What else do I know? I know that when Y is 4, it happens when t is 2. So k times 2. Okay, so what can I do now? Okay, well, I can bring the 2 on this side and write 2 is equal to e to the 2k. I might want to write it like that. It looks a little nicer for me. And I could undo both sides. What do I do to undo an exponent? I take the log of both sides, okay? So let's take the natural log of 2 is equal to, well, you know what the natural log of e to the 2k is. The natural log just undoes the e. So I'm just going to save that, writing that step, and put 2k. So now I know that k is equal to the natural log of 2 over 2. So presto, I'm done. I'm finished. I've got everything. Okay, what do I have? I've got y is equal to, well, we found c already, is 2, and then we have e raised to the, remember I told you group this stuff up here, and it's equal to the natural log of 2 over 2 times t. And I don't fiddle around anymore. Leave it alone. Okay, now I know some of you saying, I want to do something more. I hit the natural log up there. So, okay, I know you want to do it. Let's do it. Okay, now let's do some properties. Can I rewrite e raised to the natural log? And this is just, these are just, stuff we could shuffle around. And I could say natural log of 2 to, excuse me. Oh boy, too exciting. Coughing while I'm doing. And it could say times t over 2. Okay, so what did we find this was? What is this thing? That's just 2. E to the natural log of 2 raised to the t over 2 power. So now this is, watch how you write this. Group, then put 2, and then put t over 2. And I would group that one too. I'd group everything. I'd make sure I knew where every 2 was. So let's go back. Let's just check our work. If we plug in 0, will I get 2? That's obvious. 2 raised to the 0 power is 1. 2 is the answer. Put in 4. 2 raised to the 4 over 2, which is 2, which is, let's see, wait. 2 over 2. 2 over 2 is 1. 2 to the 1 power is 2. 2 times 2 is 4. Yeah, it checks. So we have a final answer. So let's be happy and let's put a box around that. Okay, now that example took a while. Let me get set up for the next one and we'll do one more a little quicker. Okay, in this problem you were given write and solve a differential equation with the rate of change p with respect to t is proportional to 10 minus t. Okay, so that's our statement. Let's convert that to an equality. So we have the change of p with respect to t is equal to k times 10 minus t. And so that's that. Okay, so now what do we do here? We go ahead and what did we do every time? Every time. We took the right side and brought it onto the left, yada, yada, yada. But let's look at what's going on. What does separation of variables mean? Everything with a p goes on the left, and everything with a t goes on the right. Everything with a p goes on the left, and everything with a t goes on the right. 10 minus t does not go underneath dp. Okay? Don't be fooled by this. This is what's going to happen. You're going to do these problems without thinking, and then all of a sudden you're going to say, wow, this I did all these steps. I did all this algorithmic steps, but I got the wrong answer. This is an easy problem. So what do we have? dP is equal to group K 10 minus T times dt. Okay, I think it would be prudent to distribute everything out here on the right. You can see you're anti-differentiating a bunch of terms. So I'm going to put K 10 times K times dt minus K T dt. Okay, is that right? I hope it is. We're going to go on national TV with something wrong. That would be bad. Okay, so looks okay to me. Anti-differentiate everything. Okay, so I'm going to go P is equal to, this is just a number. So what do we get? We get 10 times K times T minus, okay, what's the antiderivative of KT? It's KT squared over 2. Okay, now, this has a C, this has a C, but we'll only show one C. Boom, done. I fooled you. There it is. You thought you had one that was one that we've been doing over and over again, and no, it wasn't. Let's go to the next one. Okay, now, carbon-14 problems. I love them. They're a staple of everything in life because we all decay. We die. We want to figure out, somebody down the road wants to figure out when we lived. They go ahead and grab some of our body that they found that has some carbon in it, and they figure out how much carbon 14 is left, and boom, they say, ooh, this person lived 25,000 years ago or whatever. Okay, so how do they do it? Well, carbon-14 has a half-life. That means every 5,730 years, half of it decays into something else, okay? So we start out with 3 grams of it. And then how much will we have after 1,000 years? Well, obviously, it's going to be more than what? More than a gram and a half. Why? Because in 5,730 years, we're going to have a gram and a half. So we start out with 3. We're somewhere in between there. We want to know these ideas of an answer so that we have a clue whether our answer is right. But more importantly, we know situations. When t is equal to 0, we know we have 3 grams. When t is equal to 5730, we know we have a gram and a half. Those are initial conditions that you are going to have to use. So you have 0, you have 0, 3 grams, and you have then 5730, you have 1.5, okay, grams. So you got to know that. You got to use that. Okay, so let's set it up. So if it's got a half-life, okay, this is exponential decay. So the amount you have is proportional to the amount you have. So the amount of carbon you have, okay, the rate of change of carbon with respect to time is equal to the amount of carbon you have. Okay, that's great. So dC over C is equal to KT. Now, we've been doing this over and over again. We don't get to just go to the answer because we've got to show all our steps. So we have a minute and 10 seconds to do it. Okay, natural log absolute value of C equals what? This is a dt. Sorry, I missed it. This is a dt up here. Is equal to KT plus C. Absolute value of C equals E to the KT plus C. What do we do? We group that always. Now what do we do? This is now what? What's next? The absolute value of C equals E to the C times E to the KT. Then C is equal to now C1 or C. You could do it C. Now we got a problem. Oh, the problem is, what do I know C's are? Is C the carbon or is C the constant, the coefficient, or not the coefficient, but the constant of integration? Ooh, bad, bad, bad. I'm going to get rid of this C1. Okay. Ooh, I'm going to call it D. I'm just going to call it something else. I got a bad vibe about this. I really do. I got too many C's in here. In fact, I'm going to throw this one out completely. This is a bad selection for that. Okay? Bad selection. I should use A for amount. I should have started out dA dt is equal to the times the amount. That's what I should have done. Okay, so we're going to pick it up on another video. Okay? You learn from this one. Watch what you select because we're always used to C, and I don't want to confuse everybody in the world. Okay, we'll say done. We'll pick it up on another video.